Dear students, let us continue our video lectures on advanced digital signal processing. Let me share the screen. In this video lecture, let us discuss structure for linear time invariant systems or discrete time systems and their realization. So far in the previous video lectures, we have seen how to analyze the sequences, time domain sequences or signals in time domain and in frequency domain. We have also seen how to analyze the signals and systems together in time and frequency domains. We have also seen how to analyze the signals and systems or the impulse response of the systems in frequency domain through various transforms such as discrete time Fourier transform, Z transform, discrete Fourier series, and discrete Fourier transform. Okay, so now let us see what is the black box behind the system implementation. Okay, so how do we realize the system in hardware? Say, assume that finally we got some h of n. Given a specific h of n, something like, say, if I have h of n, okay, which is equal to delta n minus 2 times delta n minus 1, okay, or plus 3 times delta n minus 2, something like this. So if I get some h of n, impulse response of the system, after my analysis of input and output or giving impulse to the system, okay, how do I realize that system? Yes, essentially, we will focus this video lecture on analyzing the impulse response of the system or the transfer function of the system, or realizing the transfer function of the system, okay, through hardware. What are the primitive hardware components required for this and realization? And we will also see what are different kinds of systems we can categorize based on the frequency response or the transfer function of the system. Okay, so to start with, let us take the representation of the system, discrete time systems. So if we give x of n as input for a system with impulse response h of n, if it is LTA, linear and time invariant, we can write y of n equal to convolution with input. Similarly, in frequency domain or in Z domain, we can write y of z being the multiplication of input and the frequency response. Input Fourier transform or the Z transform multiplied by the system function. Okay, so now the other alternative representation for system is through this difference equation, which relates the output as the linear combination of input and its delayed versions, and also there may be some linear combination of delayed versions of the output as well, right? If h of z has this form, the numerator corresponds to the delays in x of z, whereas denominator corresponds to delays or the previous versions of y of n. Okay, so as you can see from this expansion, right? And this is the general form of the system, any discrete time system, not necessarily LTA system even. And this under initial rest conditions is an LTA system. Okay, so let us see, given this general description of the system where there are m components here and n components here. Okay, here m plus 1 components and n components here. How do we realize such a system? This is the corresponding transfer function of the system, as you can see, which is obtained through taking Z transform for the general form, right? And you can see this transfer function when you see y of z, it is y of z by h of z, that is y of z by x of z, that is h of z. You can see that it is a rational function in z, having numerator being a polynomial in z of order m and denominator being a polynomial in z again with order n. Okay, so if I this can alternatively written in terms of the poles and zeros as well. So the roots of this denominator polynomial gives the poles, and the numerator polynomial gives us the roots. So it can also be written, though I think we are not very much interested at this point of time. We can write this as 1 minus some ak z inverse. No, so this ak is different than this. Okay, so this and this are different. So you can see that this ek will let us write. Okay, and then this pi into 1 minus dk ck. Okay, or dk. Okay, so k equal to some 1 to m here and k equal to 1 to n here. Right, this can alternatively be written in this form, but to explicitly indicates the poles and zeros. Minus 1 here. Okay, please note that this is minus 1 only because we are writing in terms of individual terms. Right? Okay, so let us see how to realize this. Based on the system function h of z, there are two broad categories of the systems, discrete time systems. One is having only the numerator term, that is referred to as finite impulse response systems. As the name indicates, if you see the corresponding impulse response, it has only finite time number of terms in it. Okay, 0 to m, that is m plus 1 terms in it. And hence the name finite impulse response systems. Okay, and the denominator here is 1. Okay, and has no poles thus. Okay, and it will have some roots, but no, that is zeros, but no poles, except possibly at z equal to 0 or z equal to infinity. Okay, which depends upon z terms in the numerator and denominator, right? In the numerator. So as a specific example, you can see that the h of n is a second order system. Okay, where you have actually, that means h of z is a second order system where you have only 3 terms here, and this is h of n. In that case, what will happen? Y of n can be written as b0 into x of n plus b1 x of n minus 1 plus b2 x of n minus 2. Right? So this is obtained by convolution of x of n and h of n. Let us consider this and let us see further for a second order system, how do we realize? Right? And as we discussed, so the specific example with b0, b1, b2 is this for the second order system, right? And h of z is this. And you can see that there are no poles and there is only 2 roots for this system, right? Or 2 zeros. Alternative way of representing this is this second order system is through these quotients b0, b1 and b2, because the structure of FIR system is anyway determined by this, and a is equal to 0 indicates that there is no there are no poles, and hence a and a bar and b bar, these two vectors usually are representation for the standard form of the Z transform or for the difference equation, corresponding difference equation. Please note that both Z transform and the difference equation share same Z transform and the difference equation share same set of quotients. Okay, so they can be easily related through given the quotients bk, b and a. Set of quotients bk and set of quotients ak determines the whole transfer function of the system or the difference equation relating input and output. Okay, for FIR systems, we have B alone can define the whole system. Okay, because it's only finite number of terms in the impulse response, right? And thus it is referred to finite impulse response systems. Now let us review or find few examples. Okay, for IIR systems, infinite impulse response systems. That means, as the name indicates, the impulse response goes up to infinity, or there are infinite number of terms, non-finite number of terms in impulse response of the system. Okay, so an example, typical example is 1 by 1 minus az inverse. You can see there are infinite terms in it, and the corresponding the impulse response, as you see, has infinite terms. The transfer function also will have infinite number of terms as given by this, right? And hence a general IER system can have both numerator and a denominator. Each of these denominator contains poles. Okay, denominators have poles, and because of these poles, each of the pole give rise to infinite number of terms. Okay, and hence altogether it goes to infinite number of terms, right? And the impulse response goes to infinite number of terms. And this can be compactly written like this, or it can be written in this way. Yn is summation of bk x of n minus k over m terms, and summation of ak y of n minus k over n terms. Please note that bk starts from 0 to include x of n also in the summation. Whereas here y of n is here, which is being equal to the previous terms of y of n and x of n and its previous terms, right? And the corresponding impulse response we can easily write like this. Okay, so as you can see, impulse response means given any difference equation, input if it is delta function, okay, the corresponding output becomes the impulse response, right? As can be seen in writing here. Okay, also note that the number of poles, okay, here are n and number of zeros are m. And the order of polynomial, numerator is m and denominator polynomial is z. So these things will determine the order of the filter or order of the system. Okay, while realization, as now you will see that all these play an important role. So let us see now with an example how to realize FIR systems first. So take this example of finite impulse response system or the impulse response. Okay, and this is the corresponding transfer function of the system. As you know, this order is 2. Okay, and the length is 3. Number of terms is referred to as length, which is the order plus 1. Okay, now to get the y of n from x of n, anyway we do the convolution and we got this difference equation relating input and output. What do we mean by realizing a system means, if we give x of n, we should know how do we get y of n. Okay, and there should be some hardware elements, like basic elements. When we put it together, we should be able to get the structure of the system that gives the output y of n from x of n. Now, looking at this expression relating input and output, what are all the primitive components in hardware that are required to get y of n from x of n? See, x of like y of n is summation of b naught into x of n, that is b naught is 1 here, so x of n, and then it should get added to the next term. Okay, so there should be an adder required. And how do I get next term? By delaying the x of n, that is x of n minus 1. So there is a delay element that is required, and then there usually there are multipliers to the delayed versions of the signals. Okay, that is bk. So you have into 2 here, a multiplier. So essentially each of the term in this y of n, in this addition, requires a delay, a multiplier, and an adder, right? So you can see here the delays, multipliers, and adders are denoted like this. A delay is denoted by Z inverse because input x of n, if I give x of n minus 1, I will get through this. Okay, and multiplier is multiplier by whatever is the value we will write on the top of this arrow. Okay, so top of the arrow we may write here. Okay, so a means a multiplier is a. Okay, so and then similarly the adders is shown by added sign or directly simply by this. Okay, so there are 2 different ways of representing. One is through this graph, other is through signal flow graph, where we even simplify this. Okay, so now let us see how exactly we should put these, organize these delays, multipliers, and adders to get the output y of n from x of n. When you have x of n, say what is needed is x of n has to be multiplied with b naught, which is done here, right? X of n into b naught, right? Here in this example, b naught equal to 1, right? And then there should be a delayed version of x of n that is obtained through delayed. We have x of n minus 1 here. It should be multiplied with b1, it is minus 2 here, multiplied, and then there should be another delayed version of x of n, which is x of n minus 2, and then a multiplier b2. Okay, all these three terms put together, what we get is y of n. Y of n now is equal to b0 into x of n plus b1 into x of n minus 1 plus b2 into x of n minus 2. Right? This is the structure for realizing an FIR system. Okay, so if we have more terms in this, more delays will come, more multipliers and more adders. Okay, so typically if I specify the number of quotients, non-zero quotients, okay, in the FIR system, I can easily write this structure of the FIR system. Okay, so because there is a standard expression that relates input and output in FIR systems, are standard, okay, standard transfer function or the standard impulse response. Okay, relating can be written based on these. Right? Let's move on now to a general example wherein we have actually m components in h of z. This m can be any large even. Okay, and hence the order is m, the number of z power is m, and the length is m plus 1. Now, as we have seen, the primitive hardware elements that are required to realize any of the FIR systems are simply delay element, multiplier, and an adder, right? And this is directly we are representing the structure from the form we have written. This is referred to as direct form. In the sense, thus this structure is written as direct form 1 representation. Okay, so we will see why 1 here. But for now, you can understand this is a directly realized from the h of z expression, which we started with. Okay, and to realize this, what we need, we in like input output relationship, we have y of n is equal to, this corresponds to b0 x of n plus b1 x of n minus 1 and so on, right? And hence what should have x of n into b0 plus x of n minus 1 we get through delay into b1, x of n minus 2 into b2, x of n minus m into bm. All these things put together, we get actually y of n, right? Another compact version of visualizing this is simply put x of n here and take y of n from outside here. Okay, so what we are getting here is simply right, as you can see, y of n out. Okay, x of n input. Okay, as you can see, x of n goes here, and then x of n goes here, multiplied with b0. You will get first term, b0 into x of n, with a delay, x of n minus 1 into b1, second term, x of n minus 2 into b2, third term, and so on up to m terms, x of n minus m into bm, you will get the final term. All these put together, what you get is y of n. Okay, this is referred to as FIR system realization or FIR filter even, because at later point of time you see that based on the frequency response, the systems, some of the systems will act as good filters. That means they will filter out some frequencies and pass them and attenuate the rest of the frequencies. Okay, so when specifically we use this h of a design for such purpose, it is referred to as filter. So and in many of the cases or some cases, there may be symmetry between b0 and bm that can even be explored for efficiently representing them. Okay, no need to multiply 2 times. Okay, we can effectively multiply 1 time and have 2 different delays and so on. Okay, there are different efficient representation of these structures is of very importance to reduce the number of delays, number of multipliers and adders. Okay, we will see especially the movement from direct form 1 to 2 is based on that efficient representation of the structures. Let's now discuss on the IER systems realization. Okay, let us take an IER system which encompasses a numerator term and a denominator term. As you can see here, the numerator term is exactly like an FIR system, and this has poles and hence infinite number of components in the impulse response, and thus okay it was not there in FIR system implementation. When you write this in the input-output relationships, this can be compactly seen here. So let us take an example for this specific example, just to have a numbers and better understanding. And this, when we consider what we have here, in input output relationship is y of n, okay, into plus 3 times y of n minus 1 plus 2 times y of n minus 2 is equal to x of n minus 2 times x of n minus 2 minus 3 times x of n minus 1. X of n minus 2. Okay, so and y of n usually in general form can be written b naught into x of n plus b1 into x of n minus 1, b2 x of n minus 2 plus a1 into x of n minus 1. Okay, because this comes this side with a negative sign. Sorry, please note that here a general form, it comes a negative sign here. Okay, so what we have written is minus a1 into z of n minus 1 will come here. Okay, so in general form, so this is minus a1, this is minus a2. Okay, and hence plus this side. A1 into y of n minus 1 plus a2 into y of n minus 2. For this one, if you take, so I will just write a indicator from here to here. Okay, from here you can get this, right? You can get this. Now, how do we realize? See, we know how to realize this term because this is an FIR system implementation or realization. So we have x of n, b naught into that, and delayed version of x of n minus 1 into b1, x of n minus 1 into b2. This numerator term, realization of the numerator term. And assume that we got some intermediate variable vn. And from here, what we need to realize is the rest of the terms, okay, that are not there in the numerator. This amounts to delaying the output y of n minus 1 and delaying further y of n minus 2 and multiplying by, say, a1 into y of n minus 1 to create this a2 into y of n minus 2 and add them to get y of n, right? So this is now essentially realizing the denominator term, and this is for realizing the numerator term, right? So you can see here the Ier system realizations has numerator term and denominator term. Realizing both together and put together in a proper sequence will give us y of n. Okay, so you should know, given this structure, how to write the input output relationships. Okay, see, as you can see here, v of n is equal to b naught into x of n plus b1 into x of n minus 1 plus b2 into x of n minus 2. Similarly, yn is equal to vn plus, okay, y of n, a1 into y of n minus 1 plus a2 into y of n minus 2, which is written here, right? And in frequency domain, if we see, vz is equal to, okay, x of z into sigma bk z power minus k, right? And similarly, what you can see, similarly, yz is equal to vz by 1 minus ak z power minus k, which is exactly the denominator here, right? So we are realizing the numerator first and then the denominator for this structure in direct form 1 realization. Now, the question here is, can we reduce the number of delays, multipliers, or the adders that are used in this implementation? Okay, at least the delays can be reduced here. The reason is being, you can see that, see, there are 2 terms in the numerator and 2 terms in the denominator, and you can see that both of them will need 2 delays respectively. So can we have a single delay for encompassing the realization of numerator and the denominator, right? And please also note that the realization of the Ier systems also have only delay, multiplier, and adder in their whole realization. So putting together just the relays, just the delay, multiplier, and adder, you can realize any of the discrete time system. These multipliers, relays, and adders may be encompassed of op amps, okay, transistors, or any other electronic components, right? So let us now see, can we further make an efficient realization, reducing the number of delays here. See, let us first explore, if we first realize the denominator and then the numerator, see, what you can see is these delays occur side by side. Given this, is there a chance to knock off one of them? That's what we will see now. So let us change the sequence of realization. Okay, previously what we have done is first realize the numerator and then the denominator, okay, to get y of n, x of n to v of n and v of n to y of n. Now let us see, if I just change the order, so x of n, let us first realize the denominator, get some intermediate variable wn, and then realize the numerator and then y of n to get the y of n. You can see these two are in cascade, and hence they both get multiplied to give us the same h of z. Same is the case even here, right? Because this you can consider h1 of z, h2 of z. The multiplication is this, right? So in the previously, this is the sequence. Now let us see this wz is equal to x of z by this, and y of z equal to wz into summation of bz into z power minus k, summation over k. And this k goes over what? This k goes over 0, 1 to n, and this k goes over 0 to m, as you can see, right? And the specific equations in discrete time system corresponding to this is wn minus ak into wn minus k, which is equal to x of n. Similarly, yn is equal to bk into wn minus k for the second one. Okay, I would like to use these two now, okay, 1 and 2, to realize the system, Ier system, and see is there an advantage in it. The first one, say, for ease of understanding, let us consider second order systems where there are only two delays or z power minus 2 terms, up to z power minus 2 terms, and hence the first equation gives wn is equal to x of n plus a1 wn minus 1, a2 wn minus 2. Okay. Similarly, yn is equal to b naught w1 wn, okay, y of b1 wn minus 1, b2 wn minus 2. Okay, so these two now let us see how to realize. Given x of n, now what we need to do is, see, we need an intermediate variable wn. wn here is equal to x of n directly plus wn minus 1 into a1. That is, to get wn minus 1, you need to delay, right, into a1. wn minus 2 delay twice and a2, okay, and put together. Okay, similarly now to realize the out, this is the, as you can notice that the first one corresponds to what? The denominator, and the second one corresponds to numerator. Okay, so now let us see the numerator term, realization of the numerator term. That is, yn is equal to b naught times wn plus wn minus 1 into b1 plus wn minus 2 into b2. And now you can see that these delays have come, okay, one like side by side, and the intermediate variable to generate these delays is also exactly same variable. wn is needed here, so both need wn, so no need of two tabs here. Similarly, both need wn minus 1, no need of two tabs here, and hence there is no need of two delays in fact. Similarly here as well. So equivalently, what we are doing is, we are reducing the number of delays for realization, okay, and are effectively so this whole structure can be realized, this h of z can be really realized only with 2 delays instead of 4 delays, unlike in direct form 1 implementation. And this is put together is referred to direct form 2 implementation. Okay, so this is efficient in the sense that it needs lesser number of delays for its realization. Okay, and you can see the exactly whatever we had here, we also have here wn minus 1, wn minus 2, and from here wn minus 1 into a1, okay, and wn minus 2 into a2 this side, to add to this to give wn, whereas to give yn, b naught into wn, b1 into wn minus 1, b2 into wn minus 2, put together you get yn. Okay, so this Ier systems are mostly realized with direct form 2 implementation. Okay, and direct form 2 is optimal than direct form 1 realization. To take an example, so assume that we have h of z, okay, with m equal to 120 and n equal to 100. Okay, so in that case, how many delays, multipliers and adders are required for their realization in direct form 1 and direct form 2? Let us see. Direct form 1, what you need? So as you can see, it requires, okay, it's roughly, this is the direct form 1 realization. So it requires m equal to 120 means 120 delays, Okay, and n equal to 100 means 100 delays. 100 plus 120 delays. Okay, 100 plus 120, that is 220 delays. Similarly, how many multipliers are needed? So in M, you need 121 multipliers, and here 100 multipliers. So 221 multipliers, and adders here 121, here 101. So you need 222 adders. Okay, this is for direct form 1. Whereas for direct form 2, main saving is in terms of number of delays. Okay, so it is highest number of delays are needed. So among M and N. So it is enough to have 120 delays, and those 100 will be leveraged for this, like for this denominator as well. Okay, for numerator you will have 122 and have denominator 120. Okay, so put together 100. Put together you need only 120 delays, and you need 221 multipliers because the multipliers did not get reduced. Similarly, the number of orders also remains same. Okay, so this is the understanding of direct form 2 implementation of the IR systems, and direct form 1 implementation. Further, for systems having large number of terms in the numerator and denominator of h of z, or having large order of numerator denominator polynomials. Okay, what people usually we prefer is to have a cascaded structure of realization rather than realizing all at one stretch. Okay, with the extending the filters with these quotients, what is preferred is to have a used to initially represent this as a cascade of several subsystems, each of second order systems. Okay, so as you can see, this can be represented as, okay, the numerator can be represented as cascade of several second order terms. The denominator also can be represented as the product of several second order terms. The advantage in this is usually if there is a 100th order denominator, we don't know from the quotients AK, we don't know what are the poles and zeros. Whereas if you are able to write like this, it is very easy to express the poles and zeros. Also, you can control the location of poles. See, for example, if I want to have a pole exactly less than 1, in this I may not be able to enforce it. Whereas here I can easily relate this AK to the poles, A1K to the poles, and I can easily, hence I can easily control the position of poles and then assess the position of poles. Okay, because this is a second order term, I can easily split this into two terms, right? Similarly, the location of zeros are very well seen from here. So this cascaded structure, okay, for say C1 equal to C2 equal to C, easily visualizes the locations of zeros and poles. Okay, and hence this is preferred structure for implementation. Okay, also as you can see, say if I implement this, what will happen? Say H1 of Z, which will have, okay, is one direct form 2 implementation of the second order system. Okay, you can see Z inverse into B01, okay, plus, sorry, X of n into B01 plus Wn into B01 plus Wn minus 1 into B11 plus Wn minus 2 into B21. Okay, this is first one for the numerator term, and this is the denominator term. Similarly, this is H2 implementation, this is C implementation. Since each of the HK here are a second order system, we can represent them through the transpose through direct form 2 representations. Okay, and then cascade them to get the overall response H of J. Okay, the other usual practice of representation where the order is high is through parallel form. Here we split in product form where poles and zeros are very clear. We split into partial fractions. Here also the locations of the poles will be clear, but zeros you will not be able to see from here. Okay, and hence it will be sum of several second order systems, subsystems, and these subsystems, note that they are different from these subsystems. Here the denominator term contains the poles and they are roughly same as earlier, but however the numerator terms are different. Okay, and then this, since it's a parallel structure, all these can be realized in parallel and then they can be added, okay, at once to get y of n. This structure has is in implementation, but if you see the stability of this system can be will be very, the analysis through or the implementation through this cascaded form is very useful, because it not only ensures the location of poles, and it also visualizes the location of zeros. And any of the inverse system of h of z can also be easily analyzed if a system is realized in cascaded form. Okay, so what will happen from here to here if the signal flows from here to here? Okay, so, and I suggest you to realize explicitly this as a homework. These are in crisp the details of how to realize different systems, IER and FIR systems, discrete systems, and also what are the primitive components that are required for realization of the discrete systems, and what are the basic forms or structures for realization of the systems. This will give us fair idea on what exactly the hardware required and what exactly goes in the realization of the LTE systems that we have been referring to and studying to in hardware. Thank you.